Well, ready for more? Yeah, I guess it's time for class, huh? Yeah, I'm wearing a kilt and a t-shirt because that's what I wear at home. So, I should probably put on socks at some point, but I don't put on socks very often, I guess, because usually it's warm enough. I guess it's just getting colder for the week. Yeah, it's very comfy. And usually I'm the kind of person that I'm always warm. So wearing stuff like pants and putting my boots on and then wearing gloves or a jacket or whatever. It was like, why would I do that when I'm only going to walk outside for like 5 minutes? So I just wear what's simple. And that's either a kilt or shorts. Yeah, I have a utility kilt. Um, and I wear that at home just because, like, I don't know, it's more comfortable, I guess. I don't wear that out in public just because then I have to, like, I have to worry about, like, sitting on, like, other stuff, I guess I would say, with the kilt on. Anyway, let's. I'm trying really hard to, to change the conversation, and it's not really going anywhere, so. Yeah, see, I don't do the warm clothing thing. Like, even when I go to sleep, I try and keep my bedroom at, like, 60 at the most. Because I have a sheet, I have a blanket, I have a comforter, and if I get under all of those things, like it's warm. And that's nice. I like it cold on the outside and then toasty on the inside. I was trying to make an analogy of food with that, and I couldn't come up with something that you'd have really hot on the inside but cold on the outside. Like that doesn't make any sense for food. Yeah, some people don't like sheets. My apartment is so poorly insulated that I just have the heater running all the time and it's just at 60 in my apartment. But I love my blankets on my bed, but that's about it, so, okay. What are we doing? We're talking about the mole today. The mole and formulas, so we're going to do a little bit of calculations. This will be all the stuff from the lab yesterday that I was like, we probably should have already gotten to this point, but we're taking it slow. That's fine. Here's a bunch of different ways that we're going to represent molecules in this class. You've already seen the Lewis structure from 140, so this is nothing new, and this is nothing new. We're going to actually care a lot about these two models in this class. We're going to use the ball and stick model when we get to molecular geometry. But the space-filling model is going to become relevant when we talk about electronic structure in Chapter 3. Not super important. The space-filling model is going to be much more relevant when you get to organic chemistry, because in organic chemistry, you're going to consider things like sterics. Sterics are, do molecules bonk into each other as bonds twist and turn? And if the answer is yes, then molecules don't want to overlap electron clouds, because electrons repel. You can tell whether electrons will overlap by looking at the space-filling model. Whereas the ball and stick model is just a more, oh, I only care about what atoms are connected to what. So I'm just going to exaggerate my bonds and draw the atoms isolated from each other so I can see them. Down at the bottom, you can see two different representations of sulfur. Sulfur oftentimes comes as a octa atomic molecule. On the left, you can see the Lewis structure of sulfur is drawn in such a way that it looks like it's an octagon. But in reality, all those carbons are tetrahedron, so you get kind of this up and down sort of thing going along, which is much more obvious when you look at it in the space-filling model, and only a little bit more obvious when you look at it in the ball and stick model. Molecular modeling is something that we are going to do, and I've actually found a new tool to play with. So I'll introduce you to MolView when we get to unit, is it 4? Yeah, I think it is unit 4. So that'll be forthcoming. Whenever you represent atoms and molecules and sets of atoms or sets of molecules, be very careful about how you are writing out that representation. If you put a number in front of your molecule or atom, you're indicating how many of those you have. But if you put the number as a subscript after, you're indicating that those are bonded together in a molecule. So 2H and H2 are very different. This is what those would look like. Okay. So be mindful of your notation. Make sure you are not accidentally writing a subscript when you intend to write a coefficient, and vice versa. This comes up a lot on the lab that you're actually doing. So the hydrate lab, the waters are bound to your compound, and what we do is we would write something like this to show that they are loosely bound. We don't do this, because then otherwise we would say that those are actually part of the ionic structure with rigid ionic bonds, which is not what we observe. So this is instead what we write to notate that. Oops, I hit the wrong button there. I almost closed the slideshow, which we're not going to do yet. Okay. In chemical equations or in chemical calculations, you're going to be representing substances by either their elemental symbol or their formula, and so on and so forth. Sometimes we will call for a molecule of a substance as it is found in nature. And so there are 7 of these elements on the periodic table that form a diatomic molecule, and they are always just found paired together. So here they are on the screen. I'll let you look at them and try and figure out why they're called the silly 7. Hopefully you've noticed that the shape that I drew over here on the right, I mean, it kind of looks like the number 7, doesn't it? Also, the stem of that 7 is in group 7A, and there are 7 elements, but then the hydrogen's way over here. Why is that? Well, he's silly. And this totally has to do with the valence electrons, that's right. In fact, it can be shown that elements in column 1A will also form diatomic compounds. However, these are all solids. If you heat them up so they're in a gaseous state, though, something like lithium, like dilithium is actually a thing. But it only exists in the gas state. And it requires very specific conditions to achieve. We don't talk about molecular orbital theory in this class anymore. I just skip over it because we usually don't have enough time. But when we talk about bonding, you're going to see, oh, whenever I have one unpaired electron, I'm going to pair it with something else. And generally speaking, that is itself. And no, you're totally right. You have the right idea. We'll talk about that more in Chapter 4, though. For now, all that I really care about is that you recognize that, oh, whenever I refer to one of these 7 elements, I always intend for it to be a diatomic molecule. Like, we're never going to look at individual chlorine atoms unless it's like for a curiosity or calculation, because something like this, just Cl by itself, is very, very unstable. Now, when we get to quantum mechanics, we're going to look at individual atoms on the assumption that they're individual and act with their own individual properties. And I will note that specifically. But if I say chlorine and sodium react, what I am intending to say is that this happens. Note that this is chlorine, whereas this with a minus charge is chloride. And those are different. Chloride by itself is very stable and is actually extremely common. So you'll see Cl minus as a single monatomic ion floating around all the time. Like, this is table salt, this is all your intercellular fluid. Chloride is probably the most abundant ion in your body, I would think. Yeah, you could totally do Brinkelhoff. Brinkelhoff, that's what it was. I like the silly 7 just because it was a picture, and I will forget Brinkelhoff and, like, forget the I or something. I don't know. Or I might interpret Cl as Ci or something dumb. So whatever works for you. The more options that you guys have, the better. And so, like, share all of your mnemonics in the chat. Like, totally. All right. I actually want to go to this page really quickly to talk about empirical formulas. So, oops, my Photoshop didn't. It worked up a little bit. All right. When I have a molecule, we were talking about how we were trying to figure out formulas earlier on. Let's suppose that I have a molecule that's got carbon atoms in it, and it's also got oxygen atoms in it too. I'm going to represent these atoms by just colored dots here. Now, it is very hard to take apart one single molecule because I don't have molecular tweezers where I can go, boop, okay, there's a molecule. In general, what we just do is heat the hell out of everything until it decomposes. And so what you end up with is a bin that collects what you have. And so let's suppose that I decomposed a bunch of stuff, and each of these dots might represent like 1 billion molecules or something. And when I do the experiment, what I observe is that I get the following, and I'm going to be super lazy here. Hold on. Can I? Oh, I can. Look at this. There we go. Let's suppose I did an experiment and I noticed that this was my result. And so what I would notice is that, oh, okay. Oops, that's not the pen. I would notice is that, okay, I have, why am I not able to draw? Hold on, I gotta select all. Oh, did I just make a ton of layers? Yeah, I just made a bunch of layers. Merge these layers and then merge down. There we go. Okay, so that was pretty terrible. Hold on. I could notice that I have some quantity here. And then what I would notice over here is that I have twice that quantity. It doesn't really matter that I can't look at an individual molecule, because by decomposing any number of them, I can find the common ratio between them. And so what I would do is then I would say, okay, I'm going to write my formula based on what I've seen up here. And then I will just divide by the smaller of the two components to figure out the ratio of C to O. So what I have done by doing this experiment is I have determined the empirical formula of specifically this compound. Now, is this what was in the container? Not necessarily. So the empirical formula tells me the family of molecules it belongs to, and the ratio has to always be 1 carbon to 2 oxygens. So it could be this, but it could just as easily be this, or this, and so on. However, what I know that it can't be is it can't be this, can't be this, or anything that has a different ratio. So the empirical formula narrows it down to what the family could be. And then we use mass spectroscopy, which we talked about last week, to figure out the rest. If I know my molecule weighs 44, oh hey, this weighs 44, that must be what it is. So doing an empirical formula analysis by just deconstructing a bazillion molecules and atoms, and then shoving the sample into the mass spec, tells us the complete picture. So we're not going to do empirical formula calculations in this class, but we need to know what an empirical formula is. Oh, I clicked on the wrong thing. I got to go over here. So we're going to define the simplest ratio that we can get as the empirical formula. So this is like after you divide by that common factor, you get the empirical formula. So if there is a number that I can divide out, I should do that. So here in benzene, the common factor would be, well, they both have a 6 in it. I'm going to divide both by 6 here. And then this would be the empirical formula. Now, sometimes you get a weird ratio. This one doesn't have a weird ratio. Again, we're going to divide by 6 here. And so I'd get C1H2O1. So that's great. But let's suppose that I had this. What number do they have in common? Well, it's not 6 and it's not 4, but 2 is in common here. And so this is an empirical formula as well. Empirical formulas are just simplest ratios. They do not require a 1 in them. And yes, so you cannot have fractions, because if I reduce this further to this, I can't have half a hydrogen atom, because a hydrogen atom is literally a proton and an electron. If you cut a proton in half, you start getting down to the quark level of detail, which would be like an up and up and a half of a down. Or actually, an up and half of a down quark would be half a hydrogen. Like, even that, I don't think you can do that. That's about as far as I know about quarks. Like, I knew very little. Like, I know a proton is up, up, down, and I think a neutron is up, down, down. And an electron is not... electron is a quark itself. It's an electron, I think. Yeah, I've never taken that level of physics. Like, I don't know. I just know they exist. So, if you have taken a physics class, you probably know more about that than I do. I think it's cool, but I've just never sat down to listen to it. Now, what if I ask you for the empirical formula of something like CO2? I mean, there's nothing to divide out, so it's already its own empirical formula. And that is possible. Some molecules can be their own empirical formula if they just happen to be the simplest ratio. Okay. So, another thing that I want to talk about is isomerism. Mostly because isomerism is really cool. And also really weird in some cases. We're going to refer to some molecules by their isomers when we talk about structure later on and draw Lewis structures. Isomerism comes up a lot in organic chemistry. For our purposes, it's just kind of a fascinating topic to cover. But it's in your text in Chapter 2, so I do want to talk about it a little bit. An isomer is any molecule that has the same formula as another, but a different structure. So, for example, on the bottom, one of these is vinegar, the other one will kill you. But they're both C2H4O2. Which one is which? Well, this one's vinegar over here. That's supposed to be an N. I'm having the worst time writing NE today as two letters together. I'm just writing too quickly. So what's so deadly about this? This is a little bit of organic chemistry, but whatever. This is called a carboxylic acid. Carboxylic acids are acidic. They deprotonate, they lower the pH, and they do other stuff like that. This is what's called an aldehyde. Aldehydes tend to be toxic, but not always. But what's important is that the toxicity arises because they're very reactive. And so you could add stuff to it. Oh, we're going to get to thalidomide. Oh, are we going to talk about thalidomide? I'm glad that you know that, because I always forget the name of thalidomide. And I had to go look it up as, which isomer causes birth defects? So we're going to talk about that. But that's a different type of isomerism. This is just structural isomerism. So specifically, we'll be specific here. So structural isomers are same formula, different bond connectivity, we'll say. Because I want to be specific about how the structure differs here. And you can see in the circled parts, this O got moved over here. Like it's where did it go? I don't know. And as a result of that, the molecule on the right is very reactive to specific things, and the molecule on the left is reactive to other things. And it just so happens that this one is far safer for the body to tolerate than this one. Okay, so that's one type of isomer, structural isomers. On this slide, we're going to talk about stereoisomers. I have called them spatial isomers because your textbook mentions this, but what these are actually are, these are called enantiomers. And the reason that they are called enantiomers is because they are mirror images of each other. This dotted line that I'm ruining here is, we'll just write here, mirror. This is a mirror. And if you reflect the image of the molecule on the left that's labeled S across the mirror, you get the image of the molecule labeled R. And you might think, well, duh, they're exactly the same. But I've circled a very specific carbon here that actually kind of screws this all up. And so what ends up happening here, and this is hard to see in a model. I could make a model really quickly. Let me see if I can do this and actually get a model out for you. On MolView. What are these called again? I don't know what this compound is called. Carbon. I know it's like caraway and spearmint, but okay, so oh, good, I can do this. Okay, so here's Carvone Plus. And I also want Carvone Minus. Oh, but I want this in a different window because I can't put them both in at the same time. Maybe I can. Hold on. So select all. Can I copy? Copy. Paste. No, okay. Sorry, I guess I should let you see what I'm trying to do here. There we go. Oops, hold on. All right, so let's do that. And then I want to open a new tab. And, oh, wait, hold on. Is that what I want to do? Oh, I can just paste this in here. There we go. Oh, wait, never mind. Okay. I'm just being dumb. I want Carvone Minus. There we go. Okay. So you're going to notice that the difference between these two structures, let me actually put the whole structure on the screen here. So there's not much difference between the picture on the left here. But what I'm going to do is I'm going to spin this guy around so that it kind of matches what you see over there. Can you see the difference in the hydrogens? So look really closely right here and right here and right here when I do that. And you're going to notice that, oh, they sort of invert, don't they? Yeah, they totally do. So if I spin this sideways like that, I spin this one sideways like that, you'll notice that now they're very different. See how, like, it right here, instead of going down in this one, it goes up in the other one? So they have the same structure, and all the bonds are connected the same way, but their geometry in space is different. So these are spatial isomers. And specifically, if I took a mirror, so look how I did this, and then I flip it over, and it's hard to rotate in 2D. I have very limited options here. So now if I do this, and I go back and forth between these guys... Oh, I have the wrong mirror plane. Hold on. So if I go like that, and I go like that, there we go. So now, these should be mirror images of each other. And that's hard to show. I wish I could show them both at the same time, but it's not letting me do that, so... All right. Let's talk about thalidomide. I gotta find thalidomide here. All right. Here's the structure of thalidomide. Over here, we're gonna go like this, and then like that, real quick. And so you can see it's got that funky wedge stuff. This wedge indicates that this bond to nitrogen from this carbon over here is pointed up out of the page towards us, whereas this one indicates that it's pushed into the page, away from us. One of these isomers was prescribed as sort of a morning sickness over-the-counter medication in like the 1950s, 1960s. And when they administered it, they didn't know that one of the enantiomers was very bad for you. So they sold it as a racemic mixture. A racemic mixture is both isomers are present. And what ends up happening is that the top one, I believe, I gotta actually see which one is safe and which one's not. One of them is safe and the other one causes birth defects. And if I scroll down in Wikipedia, yeah. All sorts of bad shit happens. So look up thalidomide if you wanna read more about thalidomide babies, which is extremely tragic. So even a very slight change in the structure can be extremely dangerous to the body, and the reason for that is just that molecule in that shape happens to fit with some enzyme somewhere and inhibit some growth process or something like that, is my best guess. So spatial isomers are incredibly relevant to biology and organic chemistry. For us, we're just going to point that they exist. Here I have Caravone. I don't know what caraway actually tastes like. I know what spearmint tastes like. I want to say that caraway is like kind of like a licorice sort of flavor, but I don't actually know. Anyway, the change in geometry interacts with your taste receptors and you get a different flavor. All right. It's like minty fennel. Okay. So kind of like minty licorice. Store-bought lasagna. It's funny that when you say that because I kind of know what you're talking about. All right. In 140 and in high school chemistry, which everybody has probably taken at some point, I'm sure you remember what a mole is. If there's a number that you have drilled into your skull, that number is Avogadro's number. 6.022 times 10 to the 23 things is a mole. Specifically, when we were talking about using carbon-12 as a standard before for mass spec, we said that exactly 12 AMU was the mass of a carbon-12 atom. So therefore, a mole of carbon-12 would weigh exactly 12 grams. So these two that I'm highlighting are exact quantities, but this middle number, Avogadro's number, is not. So this is exact, and this is exact. But this is measured. And the reason for that is, well, if I'm counting atoms, there's no way that the rest of these are all zeros. Like, that's impossible. However, we cannot count individual atoms. We can only get so close. And so, for 4 significant figures of precision, we can do this. I think it's 6.022315 or something is up to 7. You're never going to need more than 4, so don't worry about that. All right. We should all know how to calculate conversions between moles and stuff. Since those relationships are true for carbon, it would hold that these should be true for any isotope of any atom, provided that we know what its isotopic mass is. Or if we just want to use a randomly acquired generic sample of an atom, such as, say, iron, I could just grab the atomic mass off the periodic table. And so that's the molar mass of a compound. So an element's molar mass is how many grams you need to acquire 1 mole of that. So if you grab your periodic table, or you go to P table, I gotta find mine, it's underneath my tablet here. There we go. Iron would have a molar mass of 55.845. So 1 mole of iron is 55.845 grams to 5 significant figures. That would have Avogadro's number of atoms in it. That's cool. Oh, look at that. That was the atom that I picked. Good job me. I have 118 elements to choose for. I picked the one in the frickin' example. Whatever. Molar mass of compounds is just the molar mass of all of the atoms added together. So, for example, if I wanted sodium chloride, I could look it up on the table. So sodium, oops, I have the wrong pen. Sodium is 22 point. I was gonna say 989. Oh, mine says 990. That's close enough. Where'd my pen go? There it is. And then chlorine is 35.453. We're doing addition, so we got to use the addition rules for sig figs. And there you go. So the molar mass of sodium chloride would just be the sum of those two together. Again, that's kind of a duh. Like, we remember that, Wes. Just move on. But, you know, just in case you don't. I'm going to assume that you can add numbers together. And if you can't or are lazy or whatever, well, then there's always this. So let's get Lentech here. We probably all remember Lentech from last quarter. So let me paste that link into the chat. And then we'll put Lentech on the screen here. That's not Lentech, that's the chat. There we go. I'm going to have to play around with it. So Lentech is a bunch of calculators on its website. And principally, you know, I actually don't need all this stuff on the side here. Principally, what I care about on here is the molar mass calculator. So you could type in any chemical formula you want and hit enter. And, oh, I have to scroll down. You can actually see that. It will tell you the molar mass of that. Excuse me. And so that's handy. And you can see that that's the same number that we got. Oops, I'm clicking on the wrong thing. You could see that that's the same number that we have over here. So that will save you some time. Lentech only calculates down to the hundredths place for each element and then sums them all together. So your sig figs will be correct based down to the hundredths place. Usually that's fine if you have a tiny element like H2O. Like, you'll lose a few sig figs. And if I just type H in there, like, 3 sig figs might not be enough for whatever calculation you're doing. Then you'll just have to grab the numbers off the periodic table and do it yourself. But for almost any other compound in here, you should be in pretty good shape. I mean, especially for the numbers that we work with. Okay, so, yep, there's Lentech. Lentech is awesome. Use it. Don't waste your time doing molar masses by hand. This is an online class. I'm not going to make you do everything in pencil and paper. And then we should hopefully remember how to calculate the number of moles in the quantity or the number of atoms or whatever. So we can do a calculation between moles and particles or grams and particles. So I'm going to do a few examples and have you do a few examples just to make sure you remember how to do it. So let's go ahead and do that. So how many moles of silver would be in a 154.1 gram sample of silver? Select all, delete. There we go. Oh, now it's too hot in here. Hold on. I turned my heater up to high, and now it's like 75 degrees in here, and I'm like, holy crap. Sweat my ass off. All right. Just like with all of our conversions before, you can make a little tree here. we want to figure out the number of moles of silver in this quantity of silver. And recall that the relationship between moles and atoms was this. Now, the blank you can put in whatever you want to. Well, we're doing silver, so I'm going to put silver. And then I have to figure out for the relationship of grams of silver, I have to get the atomic mass off the periodic table. So that's this, 107.87. So in other words, 107.87 grams is a mole, since that's the relationship we want here. So 1 mole of silver, 107.87 grams. All right, I just realized you couldn't see my starting number there. So let's do the dimensional analysis, where I'm going to turn grams of silver into moles of silver. Those units will cancel out, leaving me with moles of silver, which is what the question is asking me. And then let's run the numbers. 1 mole silver, 107.87 grams. And then just punch in the calculator. That's not a calculator, that's my phone. 154.1 over 107.87. 1.42857. I'll just write all those numbers down. And then we'll sig fig. So this is 4 sig figs. This is 5. 1s are exact. So I should keep 4. And that's the answer I would report. For that. Hopefully that is familiar. If any of that is unfamiliar, make sure that you are doing as many practice exercises from the back of Chapter 2. We're going to be seeing more of these calculations in Chapter 6 anyway, so you'll get a little bit more practice there too. But this should really be old hat from 140. I do not know where to put my phone. Like, oh my goodness. Okay. I have this water bottle where I normally put my calculator because the cats all through the first 2 lectures I had today would not stop bugging me. And it's like, hi, Maya. Maya wants to say hi. And then she wants to say hi 10 minutes later, and then 10 minutes later. And it's like, my students don't need to talk to Maya that much. I mean, you guys love Maya, but I gotta get shit done. Let's do another example. We're going to stick with silver because it's simple. How many atoms are in this sample size of silver? So, once I get grams to moles, I could then convert moles to atoms. Let's just get rid of all of this. I don't know why my PowerPoint or Photoshop does that. I think it's my video card. It's just old. All right. And so we know the relationship of moles of anything is equal to Avogadro's number. That should be a 2. That doesn't really look like anything. There we go. So 1 mole of silver is equal to Avogadro's number of atoms of silver. So now when I do my calculation with the sample, I could turn my units from grams to moles, and then moles to atoms. Now, in theory, you could go directly from grams to atoms, but because we're going to be doing so many calculations where you want to get to moles anyway, I have it drilled into my head that I just go through moles every time. I think that that's the better practice, personally. Especially when learning. Just turn it into moles and then turn it into whatever you need. But because this is still technically a review, you could do it however you were taught it in 140. So fill in the numbers. This many grams of silver per mole. This many atoms per mole. I'm going to need a ginormous number. Not sine. I want exponent. All right, 2.191 times 10 to the 24. Don't forget that times 10 to the 24. Otherwise, you get 2 and a bit of an atom. So this would be the number of atoms that are in that sample. All right. Those are very basic mole calculations. Let's look at a few more difficult calculations. This is still all a review. How many molecules of... I guess this is butane. How many molecules of butane are in 9.213 grams? Just in case, like, you have a butane lighter and you've always wondered, well, how many molecules are in here? I don't know. I mean, we could calculate how many molecules are in there. I don't know why you'd want to know that, is what I meant. All right, so I have a mass of butane. And I want to find the number of molecules. Be really careful when abbreviating molecules that you don't accidentally abbreviate it MOL. MOL is exclusively for moles. For molecules, there really is no abbreviation or unit, so I just write MOLEC. All right, I got 9.213 grams butane. You'll notice I'm always writing butane here, even though I'm only working with butane. I write out whatever it is I'm looking at, so that later on when I start getting a bunch of stuff involved in stoichiometry, which will be unit, like, 7, I believe, which is 162. That will help you if you just get into that practice. So we're going to convert from grams to moles, just like we said we were going to. And then moles to molecules, sorry. And I just realized I didn't put any of the conversions over there, but that's okay. So we know how to figure out grams to mole and then moles to molecules. So how many grams are in a mole of butane? Well, I mean, it's still F, right? Yeah, there it is. Okay. So C4H10. So it's, I don't know if you could read that. That's really small on my screen. There you go. 58.12 grams per mole of butane. So that's cool. I've already forgotten the number. It's literally still on my screen here, though. 58.12. Okay, cool. How many molecules are in a mole? Well, in a mole of anything, there's always Avogadro's number of anything, right? There you go. (9.54588). So 9.546 times 10 to the 22 molecules of butane. There we go. I realize I'm going through these examples really quickly because it's review. If you need me to slow down or explain something, please shout it out in the chat. Just let me know. I just realized my 9 and my 4 look kind of similar, so let me fix that. There we go. So there's our answer. Now, in the next question I ask you, related to this, how many hydrogen atoms are present in my sample of butane? And this is where writing out the fact that we're working with butane becomes useful, because now what we can do oops, I want to write the formula anyway. I was going to explain why I was writing the formula now, but for some reason I wrote butane here anyway. Now what we're going to do is we're going to make a relationship here. And we'll just do this. Well, in a C4H10 molecule, there are 10 hydrogens. And the question wants me to answer the number of hydrogen atoms that are there. So I'm just going to take this relationship and do this. In one molecule C4H10, which will cancel, there are 10 hydrogen atoms. So in this many molecules of C4H10, there must be that many H atoms. Now, this is a little bit different than what we did in 140, where I would make you turn everything into moles and then say 1 mole of C4H10 is 10 moles of H. But now that you are in 161, I can trust you with the forbidden knowledge or something. I don't know. As long as the relationship makes sense, like this checks out, right? And the units cancel out, so this unit canceled out with this unit. What could possibly go wrong, right? That's kind of the magic of dimensional analysis. If the units cancel out and lead you to the correct units, the only thing that can really screw you up is a calculator error. As long as you are making true relationships all along the way, everything works out. It works out great. And in fact, that's also kind of the secret to physics and higher level science classes anyway. If you know what the units are of the thing you're trying to solve for, you just multiply shit together until you get that unit, and lo and behold, you will probably have figured out the formula. So, like, maybe a question is asking you, like, figure out the pressure that you need to get water up to this column, and you know the water's density and how high it goes, and the gravitational constant. You could times all those things together and get pressure, which would be like newtons per square meter or something. And if those are the units that are left, the number that's also left must be the answer. So dimensional analysis is really cool like that. And that's why I encourage everybody to just get in the habit of writing out all your units every time and then canceling them out meticulously, because you'll just get the right answer. You don't have to worry about it. All right, I believe I have review problems for you to try. Yeah, here we go. So these problems here, I want you to tell me how many moles of helium are in this balloon. If the balloon has 19 grams of helium, 19.4 grams, sorry, of helium. It's a lot of helium, it turns out. You're supposed to only have 2,400 milligrams of sodium per day. How many atoms is that allowed? Let's suppose that I have an aluminum sphere that has this many atoms. What would the radius of it be if it's a perfect sphere? Here's the density. Oh, these are getting a little bit more complicated, aren't they? Yeah, you could totally solve all these problems now. If you have a headache from too much chemistry, you might take 500 milligrams of ibuprofen. How many carbon atoms are in there? These are calculations that I want you to do. We'll go over the answers in about 7 or 8 minutes, because it'll take you a second to do these. And then we'll take our break, okay? So, see you in a bit. Let me know if you have any questions in the chat. For our purposes, the volume of a sphere, this number right here, this 4/3 is exact. Pi is as exact as you write it out to be. So if you only use 3.14, that's 3 sig figs. But if you use 3.141592, whatever, that's however many sig figs you get. So, all right, carry on. How are we doing? Do we have any answers to report? Let me know. Okay, cool. Yeah, so I call the problem number 3, I call a geometry type problem. And so you're going to see probably one of these on the quiz. I'm going to give you some sort of shape and its formula, and I'll give you either a number of atoms or a mass or a density or whatever. And you have to find the missing quantity. Incidentally, if you don't know how to cubed root something, type in the number into your calculator and then raise it to the power of 1/3, just like that. Also, if you go on, like if you're typing this into Wolfram Alpha, for example, I don't know what the command is for cube root. It might be cube RT. That'd be my guess. But that, what I have typed in the chat, is the functional equivalent. So if that helps you, because you do need to cube root something in this problem. Okay, I'll shut up now. Sorry. All right, 1 or 2 more minutes. I think I went a little long here. And then what I'll do is we'll take our break before we go over the answers. Actually, you know what? I hit the wrong button here. Let's just take our break now. And if you want to keep working during the break, that's fine. You can work to Earthbound. So, mostly because I don't want to push our break off so long that then we have like a 20-minute period after. I'm in the wrong window. This is Lentech. This is Earthbound. All right. See you in a bit. We'll start the timer. All right. Let's pan this out. I don't want Lentech on my screen just yet. So let's go to... Boop, there we go. All right, let's clear all this out of the way here. All right. How many moles of helium are in this balloon? I mean, that's really straightforward, right? So I got grams of helium. I want moles of helium. And according to my periodic table, 1 mole of helium is what? I got to get the periodic table. 4.00 something. 4.0026. Probably more sig figs than we need, but that's fine. Ah! I don't know what happened there. All right, so there's my units and my answer. Let's fill in the numbers. And so I'm going to get something like 5. A little less than 5. Let's see here. Oh, my calculator turned off. That's why it's not working. 19.4. 4.847. Sweet. There you go. Easy enough. I gotta set this down. Let's get the next one out here. The daily recommended intake of sodium is 2,400 milligrams. How many sodium atoms is that? I'm going to trust that everybody knows how to do this part. Just because I'm lazy. Just what am I doing over here? I want sodium atoms. So atoms, sodium, which means that we're going to need to go through moles, sodium. And again, just do that out of habit. So we'll turn grams into moles, and then we'll turn moles into atoms. Cancel those out. That's the units of my answer. That's what I want. So let's fill in the numbers. How many grams of sodium are in a mole? 22.990? Yeah. That comes straight off the periodic table. How many atoms are in a mole? How many things, or how many anything is in a mole? That many. What do we get for our answer? Let's check. .28655 times 10 to the 22. That's probably too many sig figs. So 6. Well, I only get to keep 2 anyway. So 6.3, 10 to the 22. All right, let's get the next problem out here. I'll just put the next 2. There we go. All right, we got our aluminum sphere. And I want to find the radius. So here's what I'm going to do first. I'm going to solve for the radius. So if I do my algebra, I will get 3 over 4 pi times v equals r cubed. So I just times by 3, it goes up there. Divide by 4, it goes down there. Divide by pi, it goes down there. And so cube root of this nonsense would be the radius. So once I know the volume, which I'm going to determine the volume by using the density and the number of atoms, I can then plug the volume into this formula and be done with it. So let's do that. So I know the number of atoms of aluminum for this problem. And I want to find a volume. So I can plug it in the formula and then get the radius. So I can turn atoms to moles. Mole, whatever. And once I know moles, I can turn moles into grams. And I can turn grams into volume using the density. So the density of aluminum is 2.70 grams. Oops. Equals 1 cubic centimeter. That looks kind of like a 9. Let's do that. So this first top part should be pretty trivial. So let's start with the number of atoms that we have, which is not that many. Not 12. What am I doing? Get a very small sphere if I only had times 10 to the 12. So I'm going to turn atoms of aluminum into moles of aluminum. And then we'll turn moles into grams. So this cancels with that. That cancels with that. And then I got to go down here. I'm going to turn grams of aluminum into cubic centimeters of aluminum. And so this will get me a volume. So let's plug in all the numbers here. So atoms and moles, well, same as before. There's this many atoms in any in a mole. Aluminum, I forget aluminum. What is it? 27 something? 26.982. And then down here, this is just the density. So what volume of aluminum do I have to work with? And it should not be very big. You probably hear me tapping away at the keyboard here. Or not keyboard, but the calculator. I got 1.42 cubic centimeters after sig figs. So now I know the volume. This is V. We just punch this all in here. So let's change color for that. So R would be equal to cubed root 3 times 1.42 cubic centimeters over 4 times pi. And so I have 3 times 1.42 divided by 4 times pi raised to the 1/3 power. I did in parentheses. There we go. I got 0.697. Now keep in mind that when you cubed root a unit, you get rid of this. So cubic centimeters cubed rooted becomes just regular centimeters. There you go. That's sloppy because so this part of my screen right here that you are looking at right now, I can't actually use it because I have a window there for the layers. Actually, I could probably get rid of this window. Okay. So now I only have to worry about, oops. There. I can't use this part of my canvas, which looks really stupid, but that's okay. I ran out of space. Okay. Well, we'll go back to the top here. That's a thing that my graphics card does for... It's only Photoshop. Everything else works fine. 500 milligram sample of ibuprofen. I'm going to just turn that straight into grams. How many molecules are in here? Well, we need to know the molar mass. Let's go look that up on... Well, first let's do the dimensional analysis here. I don't feel like writing ibuprofen out every time, so I'm going to do it this way. What am I doing? That's not what goes there. There you go. So we can look up the number of grams per mole on Lentec. And then in a mole of ibuprofen, there's going to be some number of molecules, which is always the same number. So this would be, and I'm going to put this over here, the number of molecules of ibuprofen that we get. I didn't cancel these out. Okay. Excuse me. Lentec, what is the ibuprofen's formula? C13, H18O2. That didn't type it. I clicked on it, nothing happened. .206.28 is what I got. And then in a mole of anything, there's always Avogadro's number of things. That doesn't look like a times. So how many molecules were we working with here? 0.5 Avogadros. 23 divided by 20628. So I got this as my answer. 1.460 times 10 to the 21. So that's how many molecules of ibuprofen are in there. And then I know that if the formula for ibuprofen is this, then in one molecule of ibuprofen, there must be 18 atoms of hydrogen. So I can just take that relationship and do that here. One molecule ibuprofen, 18 atoms H. And so we just take our answer and times it by 18. I ran out of space there, but that's okay. There you go. We all did it. You did it. I did it. All right. That's chapter 2. Okay. So I'm going to skip over the summary stuff. You can read the summary stuff on your own. It's the last few slides. Hooray. All right. Give me a second. Let's get rid of chapter 2 stuff and go on chapter 6 so we can talk about the lab a little bit more. Boop. Oh, look at this. Remember these stupid things? Yeah. Oh, polyatomic ions. Yep, they're still here. Hey, guess what? That thing that's in red, you can ignore that. This is an online class. You don't have to memorize shit. Do. Just know where this list is. It's the start of chapter 6. We're going to use this at the end of chapter 3. And it might seem like, wow, that's not much warning, but chapter 3 is the longest chapter by far. Chapter 3 will take like 3 weeks, maybe 4. So you don't have to memorize these. Like, you just not have to reference them. That said, I would encourage you to know them because you will be using them a lot. And if you have to constantly refer back to this slide, one of these 2 pages here, then it's really frustrating. And so committing these to memory will help you deal with the nomenclature stuff that happens in Unit 4. Or at the end of Unit 3. I forget where it is. It's coming up. We do nomenclature in this class, so just make sure that you have these handy, and when I say, what is this? You don't spend 20 minutes trying to find the slides. Like, put a bookmark on this slide or something like that. Here's the rest of them. Some of these are not in your textbook. I've indicated them with a star. I like for you to know them because they're common enough. And they're really just derivatives of the chlorate series. So if you know all these guys right here, then you can get these 4 and these 4 for free. Yeah, so polyatomic ions, there they are. Try and learn them if you can. If not, have them handy on a reference sheet so that you can refer to them when you need them. Okay? All right. We don't actually do Unit 7 in this class, so I'm just going to scribble this out. We're not going to balance chemical equations in 161. You do that in 162. And quite frankly, I need the time to do Chapter 3 content. So Chapter 6 is actually really short. I guess we are doing empirical molecular formulas. That's useful because this is what your lab is about. So let's do your lab. First thing we're going to talk about is percent composition. Percent composition is just a way to represent that, hey, I have this quantity of stuff in a sample of whatever mass I select. So if my sample was 60% oxygen and I had 500 grams of it, it would be 60% of 500. Generally speaking, we're going to select a mass of 100 grams to make all those percentages really easy. So here's the formula for percent of an element. You can replace X with whatever element you want. All of your percentages for a compound should add to 100, at least to the degree of sig figs that you're given. That formula should not be new. So there it is. Let's do an example here. So let's try and figure out the percent composition of this mineral. Oh, it blanked out because I went to a new slideshow. That's right. Just to get our shake the rust out, I guess we'll say, on how to do these calculations. Okay, so percent mass of whatever X is mass X over mass total times 100%. So first, let's figure out what the mass total is. And so that's going to be 15.9 grams of iron, 26.8 grams of sulfur, and 17.4 grams of oxygen. So I'm going to add all those numbers up together. I'm going to get to go down to the 10th place, so I will have at least 3 sig figs when I add. If I had more than 100, then I would end up with 4. Looks like I got 60.1. Okay, so we're going to need that number. So if we're going to do the percent of iron, we would then say I have 15.9 grams of iron. My total mass is 60.1 grams times 100%. Now, because these are masses, they go away. We're going to just kind of ignore these units. Because I can talk about reference numbers and how we always divide by 1 over the thing. Just ignore the units for this. Cancel out the grams. And what you'll get is, looks like 25% or so. 26.5. And we do the same thing for sulfur. These cancel out, and the units just mysteriously vanish. Don't know where they went. Times 100%. 26.8, 60.1, 44.6. My 4s are all over the place today. I just don't want anyone to see that on the video and think, oh, that's a 9, when it's not. I'm trying to write under the thing that I can't write under, so let me just scroll this down. At this point, you could just subtract and figure out what the remainder is, because you know it's going to add up to 100%. Oops, this is grams total. Not that it matters, because I'm going to erase it right now anyway. 28.95, so that's 29.0. And then if you want to check, you can sum all these together. So 5 plus 6 is 11, 6, 10, 19 is 20, 4, 8, 10. So you'll notice that there's some error, and that's just due to sig figs and rounding. But it did add up to 100% relatively closely, so our calculation is pretty valid. Remember that last digit is estimated anyway, so I could have estimated it to be 0 if this was a measurement. Good enough for government work. So that is percent composition. How the heck do we do that if I'm just giving you a molecule, though? Like, what are our masses here? What the heck do I do? Anyone have an idea what masses I should be using? Yeah, there you go. Use molar mass or AMU. It's all the same, right? Okay. So now, importantly, what you need to do is you need to note these numbers here because they're part of the mass too, right? So if a single carbon weighs 12.011, 14 of them would weigh whatever, and then we'll just use AMU or grams per mole. Same thing. AMU requires less characters for me to write, so we'll just use that. Uh-oh. Well, we'll just do that. Okay, so... And for this, you can still go onto Lentech. In fact, if you go onto Lentech, it will just tell you the percent composition, which I'll show you afterward. Let's actually do the math. So percent C would be... There are 14 Cs, and each C is 12.011. So that would be my mass of C divided by the mass total. And that one I am going to go to Lentech. So what is the molar mass of aspartame? H18, N2O5. 294.30 is what it says. I didn't say what we were doing here. This is percent carbon. $12.011 times 14. 294.30. Now, because this is a counted number, this isn't going to affect your sig fig, so just be mindful of that. I got 57.137%. So most of aspartame is carbon. That's cool. H on the periodic table is 1.0079. I have 18 of them. I'm going to divide by the same number down here. I got an extra dot. Get rid of that. $1.0079 times 18, 294.30. 6.1645%. So this number actually has 6 sig figs on the top here when you do the multiplication. But this one still only has 5. 6.1645. And then nitrogen is 14.007. AMU times 2. And you guys get the gist of this by now, I'm sure. So I'm not even going to do oxygen. I'm just going to go straight to the Lentech to show you where all this is. 9.51... Sorry, I can't count. 1, 2, 3, 4, 5. 9.5189. And then the rest is O. I can't hit my eraser. There we go. Like, sure, we could do that calculation, but this is also another trivial thing. So if I just go to Lentech here, boop, there it is. And you'll notice that right here in the middle, where it says subtotal mass percent, it just gives us those numbers, right? So if I do this, oh, I'm hovering over the wrong thing. If I do this and I move this over, you can see that we're pretty darn close to what Lentech spit out. Be mindful that the H here, or sorry, no, never mind. No, these match up just fine. Sorry, I thought the one that we didn't do was in the middle there. So there's our C, there's our H, and there's our N. This is what we would have gotten for, oh, you could check your work if you want. So yeah, that's mass percentage. Nothing super exciting there. Let's get that off the screen. And this on the screen. Okay. Cool. Why do we care about that? Because sometimes percent composition is a quantity that is just given to you. For example, if somebody does elemental analysis, this is a very common thing in laboratory work, is you send off your sample of your compound for EA, and what they do is they send you back the percent composition of what you sent them so that you can verify what it is that you think you have. For example, if I have a specific formula like aspartame, I should have these percentages. So if I send over my aspartame to EA and they tell me, oh, this is the percentage that you have, and I can then translate those percentages back into this formula by working backwards. So like I could say, oh, if I have 57.14% carbon, that's 57.14 grams of carbon per 100 grams of sample. Turn that number of grams into moles, and etc. And that's actually what we're going to do in the next section, is with empirical formulas, we can take percent masses and work backward. So that's going to be the point of this. And this is actually kind of what you are doing in the lab, minus the whole percent part, because you're not doing elemental analysis, although you could. Since you're isolating all the elements individually, you could just divide by the total mass that you started with your copper chloride sample, for instance, and say, oh, okay, well, if I weighed out 3 grams and I got 1.5 grams of copper, half of my sample was copper. Cool. All right. Now, this is the discussion that we had earlier today, where I drew the little bins of carbon and oxygen. I actually forgot that this slide was coming up, so I would have normally drawn this bin here and shown that if you have a bunch of molecules and you decompose them all, you'll find the ratio between them by just dividing the total number of atoms, which, of course, you could just turn into moles. So if I know the number of moles of each element, and I can determine moles pretty easily because I can turn grams of my stuff into moles, I can then figure out a pseudo formula. So let's do an example of that to show. Oh man, I hate when I draw pictures and they're already there. So we've already talked about all of this, so that's fine. Let's show an example of this. Let's try and figure out the formula from elemental analysis that gave us these quantities. And so what we would do, since we're given masses, we're just going to convert them all into moles. That's very trivial. So 1.17 grams of carbon and 0.287 grams of hydrogen. So we'll turn each of these into moles. So grams of carbon, moles of carbon. In a mole, there are this many grams according to the periodic table. What quantity do I get here? 1.17. 12.011. 0.0974. So that's how many moles of carbon are in the bin when we split this all apart. Let's do the same thing for hydrogen. Let's turn that from grams into moles. And a mole of hydrogen is 1.0079 grams according to the periodic table. And the number of moles there is 0.284. Yeah, that's right. Oh, 285, actually. Okay. Once you have everything turned into moles, here's what you're going to do. You're going to make a formula with these numbers. And it's going to look really stupid. Because what formula has all these decimals in it? Well, no formula does. So this is called a pseudo formula. Because it actually is a formula. It's the ratio of atoms to each other. But it's not really a formula in the sense that this is a physical thing that can exist. Like, you can't have a fractional atom. So to get from the pseudo formula to the formula, we're going to divide by the smallest number of moles. And that'll give us the formula. So let's do that. What's the smaller number, 0.0974 or 0.285? It's 0.0974. So I divide both of those numbers by that. So these two divided by each other give me just carbon by itself, because 0.0974 divided by itself is 1. And then for H, 0.285 divided by 0.0974 should give me a number that's really close to an integer. I didn't really get one that was super close. I got that, but that's kind of close enough for our purposes to say, okay, it's probably this. In most of the problems that we're going to be working with, you're going to get numbers that looks a lot like a 2. Hold on. In most of the problems that we work with, it's going to be a lot closer to a whole number. And we're going to do a few examples where you have to be careful about rounding, because if, for example, I had gotten this instead, should I round that? What's implied by here is that if you get something that looks like a fraction, so for example, this would be 1.5 or 3/2. You could multiply everything by the denominator to get rid of that fraction. And then this would be an empirical formula instead. So if you get to the formula part and you still have a decimal, and that decimal can be represented as a fraction, you may have to multiply to clear out the fraction. So that is something that may come up in a little bit. We don't really have that much time for more than one more example. So let's do one more example and then we'll call it a night here. Oh, here we go, fractional results. Let's do one that gives you a fractional result. I'm just looking at this and I immediately know what the answer is because I know these molecules. What am I moving? Oh, that's Lentech. I don't care about that. There's like a mysterious window over my OBS, and I was like, what is it? All right, so a sample contains 10.62 grams of chlorine and 16.80 grams of oxygen. Determine the empirical formula. Now, remember before when I said, hey, we're going to assume that chlorine is Cl2. In this case right here, treat it as Cl, just because that's what it's being represented as. If I were to write Cl2 and you turned it into moles of Cl2, then what would end up happening is you'd get half as many moles, because the molar mass of Cl2 is double that of Cl. And then when you're writing it in the formula, you aren't writing Cl2s in the formula. So, like, we're not going to have this and then a number after it in our formula. We're trying to get CL. So this is not supposed to represent CL as it appears on its own in nature. This is CL that's in a compound. So dealing with it as an individual atom here is actually required. 10.62 grams of CL. All right. And I have no idea what this one is. 35.453. All right. So it looks like we're going to get a third of a mole. Uh, 0.2996. Make that a little bigger. Okay, cool. Let's do that for oxygen. What's oxygen? 15.999999? 15.999. Okay. Okay, cool. So we got the number of moles. Let's make a pseudo formula. So Cl 0.2996, oxygen 1.050. I'm going to divide by the smaller number. And that will give me my formula of Cl 1, and then O, I gotta actually do the division. Oh, look at that, I get 3.5. It's just kind of like what we were talking about before, huh? 3.505. That is so close to 3.5 that I'm just going to do this. We're going to round it to 3.5. Now, obviously, you can't have half of an atom, but if I times it by 2, 3.5 would become a whole number, right? And so my empirical formula here is this. Now, how do you know when you have fractional results and you need to do this multiplication? There are a few fractions that are common enough that you should just watch out for them. And so let's just put a bunch of C's and H's together and do this. So one of them is if you have something that ends in a 0.5. That's obviously something you can represent as a fraction, and then you'll multiply it by 2 to get rid of it. Other ones that you can come up upon would be something like that, which would be 1 1/3 or 4/3. Well, you just times it by 3 to get rid of that. So if you see numbers that look like fractions, now you know how to get rid of them. Now, you could technically do this for every number. You could go all the way down to like 25 or 30 or whatever. But in reality, you're not going to get problems that have integers that are higher than like 5 or 6. Or not integers, I'm sorry. You're not going to have problems where you have to multiply by a number higher than 5 or 6. So for 5, that would be 1.2. You could get rid of that. Now, with regards to your lab data, I've given you lab data that works out pretty closely, and so you won't have to worry about, oh, does it land on like 1.18? Should I round to 1.2? Or is that close enough to 1? So you won't ever encounter that with the data that I've given you, just because I wanted to try and avoid that. If you were doing the experiment yourself, and you had a systematic error somewhere, excuse me, then what could happen is that, well, maybe you have too much water, and so all of your masses get messed up, and so then who knows what the answer is. And as a result, you'd get numbers that aren't even close to being rounded to anything. That is a thing that happens. So my advice is, when you are doing empirical formulas, if it's a theoretical or textbook problem like this that we're doing now, be stingy with your rounding and try and scrutinize it. Look for fractions that you can multiply away to get an empirical formula. So like this. This might happen on a theoretical problem. On an experimental problem, so like you do the experiment and your data is what you collect, round generously. Okay? So if you had collected data and you got a number like CH 1.14, I would round that to 1 if that was an experiment, because it's very hard to get reliable experimental data, especially if it's your first time in the lab. But the numbers that we generate here are theoretical. These are not numbers that people got, unless they did like 17 experiments and that took the average. All right. So that's how we deal with empirical formulas and figure out formulas from data. I think I have practice problems for you to try. But we're going to start tomorrow with these and then do empirical formulas and molecular formulas by using mass spec. So I'm going to stop here since we're pretty much out of time. I don't think that 5 minutes is enough for you to do the problem and for us to go over the answer, and it's kind of a bummer if you don't get to see the answer. So we'll just do it tomorrow. Whatever, right? I want to thank everybody for coming out to the lecture tonight. I realize it's late, and we're all hungry, and it's cold, and we're all so very alone from this pandemic. And now you must leave me for another day. I don't know what I will do. I guess I will just play this music. This music is the only thing I have. Have a good night, and we'll see you tomorrow for the rest of Chapter 6.